This is for lesson 9 and a cool down called Interpreting Exponential Functions. So earlier in this unit we had used equations to represent situations characterized by exponential change. For example, to describe the amount of caffeine C in a person's body T hours after an initial measurement of 100 milligrams, we use the equation C equals 100, the starting amount, times 9/10 to the T power. 9/10 was the fraction of the caffeine that was left after 1 hour. So if 9/10 were left, that means that they're losing 1/10 for every hour, or it's going down by 10%, or it's holding on to 90% of the amount of caffeine after each hour. Now, notice notice that the amount of caffeine is a function of time. So another way to express this relationship is C equals f of t, where f is the function given by f of t equals 100 times 9/10 to the t. Now, if you'll remember this week in our previous lesson, lessons 7 and 8, I showed you how to use Desmos to type something like this in to make some calculations. We can use this function to analyze the amount of caffeine. For example, when t is 3, the amount of caffeine in the body is, well, that. And then 9/10 to the third would be 729 over 1,000. Multiply that by 100, we get 72.9. Or we can go to Desmos, and we can say that the medicine as a function of time is equal to 100 times 9/10 to the T power. 9/10 to the T power. There we go. And if I wanted to find out what it was after 3 hours, I could just do m of 3 as well. So that's an option that you can use. Now, we can also use the graph of f to better understand what is happening. So if we take a look at this, we started with 100 milligrams, and after that we went down to 90 because we had 9/10 left, and it keeps going. Or we could also just look at over here, when time is 10 hours, our amount of caffeine is just going to be a little bit less than 20, 30, 20, 40, 60, 80, a little less than 40. So 35 is pretty good. Now, a graph can also help us think about the values in the domain and range of a function. Domain being the possible inputs or the numbers on our horizontal axis, range being the possible outputs or the vertical numbers on our axis. Because the body breaks down caffeine continuously over time, the domain of the function, the time in hours, can include non-whole numbers. We can have an input of 3.5 for 3.5 hours after we took our dose of caffeine. In this situation, negative values for the domain would represent the time before the initial measurement. So let's say Mr. Van drank a cup of coffee at 8 a.m., but we didn't measure the caffeine in his bloodstream until 9 a.m. We could put in -1 to find out the amount of caffeine in Mr. Van's bloodstream 1 hour before we started measuring. The range of this function would not include negative values, because a negative amount of caffeine doesn't make sense in this situation. So let's take a look at the cool down that I'm going to ask you to do. This graph shows the bacteria population on a petri dish as a function, f, of the days since D, an antibiotic, is introduced. There's a couple questions here for you to interpret values by looking at the graph. What is the approximate value of 4.5, or f of 4.5? Remember, if the number of bacteria is a function of the number of days, this is a number of days. This is asking for the amount of bacteria after 4.5 days. Look at your graph and see if you can figure it out. Approximately what was D when f of D, so when my number of bacteria on some day was 400,000? Well, 1, 2, 3, 4. What day would that be on? And then, looking at this graph, it's asking us, what would we do using graphing technology to be able to see f of 15 on the graph? This was another thing we did in class. Remember, when you go to Desmos, if you click on the little wrench icon in the top right, you can adjust your window. You can adjust the x values you're looking at. You can adjust the y values that you're looking at. So what would you have to do here in order to be able to see what f of 15 is? I hope that helps. If you have any questions, let me know.